Okay, so this is going to be a long video on how to do the Chapter 4 naming worksheet. I hate doing long videos, but I think this one might be pretty necessary. So before we get started, I'm going to show you how I would do the periodic table and utilize it if I were given it on an exam. So the very first thing I would do, especially if there's going to be no naming or nomenclature, is I would go through and make sure that I add appropriate charges to each column. So this is going to be my 1+ column. 2+, 3+, 4 plus or minus, 3 minus, 2 minus, 1 minus, and 0. All right, once I have my charges all written, I also want to make sure I understand where metals and nonmetals are separated. So go like this, draw my little stair stepper. Now semi-metals are going to be here, 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 and here. This guy's kind of up in the air. People debate about it, whether it's a metalloid or not. Okay, so here I've got my metalloids, or semi-metals. Up here, my upper right. Up here in my upper right, I have nonmetals. And anything under the stair stepper and to the left are going to be my metals. Hydrogen's an exception. Hydrogen is actually a nonmetal. But oftentimes in acids, it's going to ionize. As an example, acid will ionize and it'll become an ion. And so that's why we care about it being in this column over here. All right, so then I'm going to do another thing. I'm going to look at polyatomic ions. So the first thing I do on my periodic table, I'm actually going to zoom in quite a bit, is I add an oxygen to chromium, I add an oxygen to manganese, I go over here, I add an oxygen to carbon, nitrogen, phosphorus, sulfur, chlorine, bromine, and iodine. So I add an oxygen to all of these. Once I've added an oxygen, I'm going to go ahead and add the charges. I look at things in terms of how many are in there. I have 2 things here, so I'm going to make this a 2 minus, and this a 1 minus. Over here I have 2 things as well, so I'm going to say this is a 2 minus, this is a 1 minus. Here I have 3 things, the Po, So, and the Clo, so this is going to be a 3 minus, 2 minus, and 1 minus. Here I have a 1 minus, and here I have a 1 minus. And last but not least, I'm going to look at the number of oxygens I'm going to add. So here I'm going to, what will be a chromate, I add a 4 and a 4. PS, these guys get 4 and 4 as well. And everything else gets a 3. 3, 3, 3, 3, and 3. And what these are, they're my 8s. This is chromate. This one's really funny. This is the only one that's different. This is a permanganate. Here I have carbonate, nitrate, phosphate, sulfate, chlorate, bromate, and iodate. If I want to go from an 8 to an 8, for example, chlorate is ClO3 negative. Chlorite will be ClO2 negative. You simply lose an oxygen, but the charge stays the same. You can check out Polyatomic Ion video if you want to for more information on that. All right, now some other things I'm going to think about before I begin this worksheet is the following. I have essentially 3 types of compounds I'll be looking at. I'll be looking at binary covalent. Those will be 2 or more nonmetals. And when I get 2 or more nonmetals, that's the only time I'm allowed to use di, tri, tetra, etc., all the prefixes. I'm going to look at ionic compounds. This is when we have a metal and nonmetal. And in the case of an ionic compound, this is when I'm going to be looking at charges. You can't use di, tri, tetra. You're going to be looking at charges canceling only. And then we'll have acids. Acids are molecular compounds, but they ionize into H plus and whatever the conjugate base is. We'll talk about that later in general chemistry, but for the most part, they're going to start with H, then they're going to have something, some kind of component, and then it's going to end with aqueous sign, meaning it's dissolved. So anytime we got an H and it's aqueous, we know it's going to be an acid. There are two types of acids, but you can watch my acid video for that. We're going to get kind of go straight for the throat here and start naming some stuff, given this information that we now know. All right, so the first one we have is N2O3. If we look up at our periodic table, nitrogen's here and oxygen's here. They're both in the non-metal section. So the non-metal section allows us to use di, tri, tetra, etc. That's what we're going to do. This is going to be called di-nitrogen, tri-oxide. The next one is barium permanganate. Barium permanganate. Well, some interesting stuff we should know about barium permanganate is that we know barium's charge. It's right here. And we should also be paying attention to the fact that barium is a metal and a non-metal. So as soon as you see metal, be thinking about charges. Any kind of metal, anywhere in here, we're thinking about the charge. So here, when it says barium, I'm thinking, hey, this is actually not going to be neutral barium. This is barium 2+. And permanganate. Wait, what's permanganate? Oh yeah, you literally wrote it right here. It's MnO4, and it's got a -1 charge. Now you just need to cancel out the charges to get your neutral compound. So in looking at this, I got a 2+ here, a -1. We need 2 of these -1s. Anytime you have more than one polyatomic ion, you're going to want to use parentheses to represent that, because you want it to be 2 entire permanganates. These things stick together. And this is my answer right there. Now we want to name this thing. What is tungsten? But anytime we name an ionic compound, we want to see if we know the charge of the metal or not. Barium, we knew the charge because it was in the second column. But this tungsten, we don't know the charge because it's actually right here. We don't know its charge. And so when we go to write it down, we're just going to say tungsten for now. But we do know carbonate. Carbonate is CO3 with a 2- charge. So if it's CO3 with a -2 charge, and there's 2 of them, your total from the carbonate is -4. If my total from the carbonate is -4, that means my total from the tungsten has to be +4, and that's why our answer is tungsten 4 carbonate. One other thing I forgot to mention is that there are some exceptions to the metals. Anything under the stair stepper, we don't know the charge of, but we do know the charge of these 3. There's 3 of them, and the charge of them is going to be 3+. Here we have zinc and cadmium. There's 2 things here. These are going to be 2+. And here we have silver. It's 1 thing. It's going to be a 1+. So notice this little 3, 2, 1 kind of a stair step there. These are 3+, 2+, and 1+. And that's also good to know in case you run into it. Any metal outside the first or second column that's not in the stair stepper, we don't know the charge. All right, move on to the next one, OF2. Well, OF2, they're both non-metals, and that's the only time we can use di, tri, tetra, etc. This is oxygen, difluoride. Not monooxygen, we never start with mono. And now we get really into the meat and potatoes. Ooh, I'm so excited. Acetic acid. What? All right. So there are two types of acids. Acids that start with hydro. Let me write it over here. If it starts with hydro, it's simple. But if it's no hydro, it's going to be a longer acid. It's going to be with a polyatomic ion. It's called an oxyacid. And it's going to be with a polyatomic ion. So here in acetic acid, there's no hydro. So I'm going to be thinking about a polyatomic ion. Well, the phrase in class that we talked about is, if you ate the ick, you got the itis. So our ates become ick, and our ites become us. So going back over here, it says acetic acid. If it's acetic acid, that means it was originally acetate. So it's a polyatomic ion, acetate, made to be an acid. As soon as we see acid, we think H+. Paired with this polyatomic ion acetate, which we should know is C2H3O2 negative. And you just need one of each, H, C2, H3, O2, and it's going to be aqueous. And that's our acid. That's acetic acid right there. Now, we come across this, and we should note that it starts with an H, and it's aqueous. Those are the two requirements for it to be an acid. So right away over here, we can say, hey, we know at least it's going to be an acid of some sort. The next question is, what kind of acid? Well, it looks to me like this is a polyatomic ion. So that means we won't have hydro in it. It's just going to be a straight up changing the ending. So this right here comes from CrO42 negative, which we wrote down on our periodic table as chromate. But remember, when we make it an acid, we change the ate to ick. And that's why this is chromic acid. Moving on to copper 2 sulfate. Copper 2 tells us the charge of copper is Cu2+. It's 2+. Sulfate, we wrote down on our periodic table. Right here, it's SO4 2 negative. We just need one of each to get the 2+ to cancel with the 2-. And CuSO4 is copper 2 sulfate. Moving on to N2S5, we should recognize that these are both nonmetals, and that's why we can use prefixes. This is dinitrogen pentasulfide. Then we get to this one. Well, we know that copper 2 sulfate was this thing, but now we've got copper and sulfate again. So what kind of copper sulfate is it? Well, we know sulfate is SO4 2 negative. Okay, so we know that sulfate is SO4 2 negative, and we have to figure out the charge of copper so we can write it in Roman numerals when we get over here, because we don't normally know the charge of copper. It could be a variety of things. And so sulfate is SO4 2 negative, and we're trying to figure out what copper is. Well, we know we have two coppers, and we know that they have to cancel out this 2 negative charge. So therefore, the total charge from this copper must be 2 positive. Because there's two of them, each of them must be positive 1. And that's why copper 1 sulfate is this. So copper 1 sulfate. To drive this point home, I'm actually going to work backwards. So let's say we only knew it was copper 1 sulfate, and we're trying to draw it over here, write the formula over here. Well, copper 1 would be Cu+, and sulfate is SO4 2-. So we would need 2 coppers to cancel out the SO4 2-, and Cu2 SO4 would be our answer. That's copper 1 sulfate. So kind of going both ways, it's important to see how that works. And now we get to here. This is commonly mistaken as an acid. I noticed a lot of students saw this and thought, hey, there's an H, but is this thing starting with an H? The answer is absolutely not. And instead, is starting with potassium. Potassium is a metal. That tells you that this is actually an ionic compound. So we have potassium, which is K+, and this other thing, HSO4. Well, according to polyatomic ion table, or the video for the polyatomic ions that we have posted, this is actually called either bisulfate or hydrogen sulfate. And it's actually its own polyatomic ion, HSO4. And so that's why this could be called potassium bisulfate, or probably more effectively potassium, we'll call it potassium hydrogen sulfate. All right, the next one here we get, this is lead, this is some oxalate. We don't know the charge of lead, but we do know that oxalate, C2O4, has a 2 negative charge. Because there's 2 of them, this must be a positive 4 to cancel out the negative 4 coming from over here. So this is lead 4 oxalate. Tin 2 dichromate. Tin 2 is SN2+. Dichromate is Cr2O7, and it has a 2 negative charge. So we just need 1 of each to cancel this out. All right, now we're going to look at the next one, aluminum phosphide. Aluminum is a charge we should know. It's got a 3+ charge. Phosphide is commonly mistaken for phosphate or phosphite, but these endings are really important. It's "ide." So we're actually going back to the periodic table. Well, in the periodic table, phosphorus, when it becomes phosphide and takes on 3 electrons, it's a 3 negative charge. And therefore, we just need 1 of each. And ALP is our answer. We get over here, SO3 with a 2 negative. I can see that this is an ion. It's got an overall charge. If you look at pretty much everything else here, it's a compound. It doesn't have an overall charge. So we get to this, it has a charge. And what that tells me, hey, it's many atoms and it has a charge. It's a polyatomic ion. And that polyatomic ion has 1 less oxygen than sulfate, and therefore it is sulfite. You could even write sulfite ion if you want to. It's a little bit redundant. And now we get to this. Oftentimes people look at this and they say nitrate. I purposely put this one directly after the sulfite because I want you to take a second and ask yourself if it really is. Is it a polyatomic ion? Because an ion has a thing with a charge, but this has no charge. And we actually asked this question in class before, and you got it right because I hadn't taught you polyatomic ions yet. So this is a nitrogen and 3 oxygens, and that's why it's just nitrogen trioxide. The next one's pretty straightforward. Disulfur trioxide. Disulfur would be 2 sulfurs, 3 oxygens. And the next one, hydrophosphoric acid. Hydrophosphoric acid tells me that there's no oxygen. This is not a polyatomic ion. It's not a pit. So instead we're looking at an acid where we have to pay attention to H+, and something from directly from the periodic table. That thing would be P3-. So we need 3 H's to cancel out that P3-, and H3P, we'll go ahead and make it aqueous, would be our answer. Next we have phosphoric acid. Phosphoric acid, I purposely put this here in case you accidentally put phosphoric acid for this one, you'd hopefully see the difference. Phosphoric acid doesn't have a hydro, therefore it's coming from the polyatomic ion. Phosphoric was originally from something that had 8. Remember, if you ate the ick, you got the itis. So if it ends in 8, or if it ends in ick, it was originally from an 8. Well, phosphate is PO4, 3-. Don't forget that we're making an acid. Acid is H+. So we need 3 H+, and therefore H3PO4, aqueous, would be our answer. We go to phosphorus. Phosphorus had to have been from a phosphite acid, and therefore we simply draw phosphite. It's PO3, 3-, 1 less oxygen than phosphate. And we need 3 of those hydrogens to cancel it out. And our answer is H3PO3 aqueous. Now, in case these didn't help you clarify, when we get to this one, oftentimes people have seen hydrochloric acid so much, which is HCl, that we get excited and we draw HCl. But this doesn't have hydro, therefore it's a polyatomic ion. No hydro. Tells you it's a polyatomic ion. And so all we have to ask is which polyatomic ion is there? Well, it's Ich, so that means it's originally 8, so we're looking for something made out of chlorate. Chlorate, we know is ClO3 negative, and we just need one H plus to cancel it out. And that's why HClO3 aqueous would be chloric acid. Finally, we get to this one right here. I see a charge, so that charge tells me that it's probably a polyatomic ion because there's many ions and it's got a charge. And in going back and thinking about this, just to drive this point home, IO3 negative is iodate. We clarified it when we first did our periodic table. Therefore, let's go this way actually. IO2 negative would be iodite. IO negative, one less, would be hypoiodite. Just like when you have low blood sugar, you're hypoglycemic. And to the opposite effect, if we've got an iodate, we can add one more oxygen. The opposite of hypo is hyper. And that's why this is per iodate. We drop the hype. And so that's why this answer right here is per iodate. Notice they all keep the same charge, they just differ in the number of oxygens. All right, I think that's it, y'all. Only took me 1 week to put this whole video together, so have a great one and stay safe. Bye.